All right, in this video, I'm going to cover section 2.3, Newton's method. All right, so the last time we learned the fixed point iteration methods, right? So in a fixed point iteration method, the definition um, how to define function g, it will affect the convergence and then efficiency of the fixed point iteration method a lot. So the best way to define G was to the was introduced, right, and the example, the last the lecture note, section 2.2 fixed point, and then that was based, that definition was based on the Newton's method. So we're gonna study the Newton's method so we understand why example, the fixed point iterations, example, the x minus derivative function f divided by derivative f, that definition of function g, why that definition will give us the best the result in the fixed point iterations. Okay, so here in Newton's method, you can see that give a second. So Newton Raphson method is one of the most powerful and well-known numerical method for solving root-finding problems. Keep in mind this: we're still the deal with a root-finding problem. Okay, so introduction to Newton's method based on Taylor polynomial. So we're gonna derive Newton's method based on Taylor polynomial. So suppose that f is a c2, you know what c2 means, right? So up to second derivative, a function f is continuous on closed interval a comma b, okay? And the p0 will be a approximation, actually, approximation to the solution p of f of x equals 0, such that f prime p0 is not equal to 0, and the p minus p0 is small. So let's take a look at this. Okay, small. Okay, we're gonna yeah. So you know, finally we end up with dealing with this one. Okay, so anyway, so let's see. Consider the first Taylor polynomial for f of x expanded above p0. So then f of p gonna be the Taylor, the Taylor polynomial series, right? Taylor series. Okay, so and then Taylor polynomial can be written as like this: f of p0 plus p minus p0 times f prime plus p minus p0 square over 2 times f second derivative cosine p. So the last term can be considered as a remainder. I mean, the truncation error is called truncation, or error, or is called the remainder term, right? So now then, this one, f of p0 plus p minus p0 times f prime, is first Taylor polynomial, right? Okay. Well, definitely cosine p must be between p and p0, or p0 comma p. We don't know p0 on the left hand side or right hand side. I mean, greater than p or less than p. Okay, anyway. So since f of p equals 0, so we assume that p is what? The solution. I mean, yeah, solution of the root finding problem. So since f of p equals 0, then this equation gives, see, f of p equals 0. Okay. So let's see. F of p equals 0. So we got this 0 is equal to f of p0 plus p minus p0 times f prime p0, and then truncation error right there. So the truncation term can be ignored because we assume, they see that? We assume that what? P minus p0 is small. Not just small, it's really small so that we can ignore. So almost 0. So since p minus p0 is almost 0, so really small, take a square, then the real small, right? So the truncation error can be ignored. So we got this: 0 is equal to f of p0 plus p minus p0 times f prime. Now, so here, okay, so keep in mind this p is unknown, by the way. So we're gonna solve that equation for p. Then we're gonna get this. Okay. So now, so P0 is, let's considering that P0 is the initial approximation, then we plug in substitute initial approximation P0 into P0, okay? Then we're gonna get the next what the approximation P1, okay? So now you see that so the back to the fixed point iteration method, considering the Pn as the the sequence of this approximation, then P sub n can be obtained by P sub n minus 1 minus f of Pn minus 1 over f prime Pn minus 1, right? So that's why the definition of, remember the definition of function g? So remember that here, the in the section 2.2, the last example, once we define g function g as like this, and then that this one gave the best result, right? So now you figure that why we can understand that why that definition gave us the best result, because that definition um, was defined based on that one, that Newton's method. Okay. So now the note that P sub n is the x-intercept of the tangent line. It makes sense, right? So the let's see now. Let me see. Okay. So we can consider that what? Give me a second. Yeah. So I mean, I think right here. Yeah. Okay. Sorry. So now then, why Pn is the x-intercept of the tangent line to the graph of f? Yeah, because the give me a second. I mean, so let's say, think about this. Let's say graph of f is like this. Okay. Let's say this is a graph of f. Okay. So here x-axis, right? And then Pn minus 1 here. Okay, so let's say here is a Pn minus 1. Okay. And then right here, this is the point whose x coordinate is Pn minus 1. Okay. So now then the tangent line gonna be this. Right? This is gonna be tangent line right here. Then let me extend the x-axis like this. Okay. So then let's figure out the equation of that tangent line. The equation of this tangent line gonna be what? The let's see, f. Let me use y. Okay, y. Okay, y is equal to y minus y0 is equal to m, which is slope of tangent line, times x minus x0. I use the point slope form. Remember that in the algebra. In closed algebra, there are three type of the equation, three form of equation line, right? This one of them was the this point slope form. Now, since we know that that tangent line passed through the p sub n minus 1 comma f of p sub n minus 1, so I'm going to replace the this should be x naught. Okay, sorry. Hmm. Oh, I'm sorry. Oh, no, the eraser right here. I'm sorry. So this should be not 1, but actually x naught, right? Yes. Oops. It should be x naught. X naught. Okay. So, all right. So now then, Then we're gonna get this. Y minus y. Give me a second. Yeah, so here, let's say this is graph right here, and the x-axis, and the p sub n minus 1, and let's say this is graph of f of x. Okay, so now the point, the coordinate is going to be n minus 1, comma f of p n minus 1. And then this is the tangent line. Okay, y minus y naught. Y minus y naught is equal to m times x minus x naught. Okay, now plug in p n minus 1, f of p n minus 1 into the x naught and y naught. Then we're going to get this y minus f of p n minus 1 is equal to m times x minus p n minus 1. Okay, then what's the m? We know that this is what? F prime, right? Or p n minus 1, right? The x minus p n minus 1. Okay, now then let's figure out the x coordinate of the x-intercept. We see the x-intercept right there. This is x-intercept of the tangent line, right? So in x-intercept, y coordinate must be 0. We know that. So I'm going to plug in 0 into, and then here, okay, right here. Okay. Now then, give me a second. Then let's say now then we'll get this 0 minus f of p n minus 1 is equal to f prime of p n minus 1 times x minus p sub n minus 1. Okay. Then now I'm gonna isolate x. Okay. Then when you get we're gonna get this x. Give me a second. X is equal to then p n minus 1 minus f of p n minus 1 over f prime of p n minus 1. Okay. Now you see that here we in the handout, see that we did denote this one as Pn, right? So it should be P sub n. Okay, so P sub n is nothing but what? X coordinate of the x-intercept of the tangent line at P sub n minus 1. Okay, then you understand, then you can figure out that what does P sub n plus 1 means. P sub n plus 1 is going to be what? It's going to be, excuse me. So now then we're gonna find out tangent line at P sub n. It's gonna be this. Okay. So here. Okay. So now we see this point. That's gonna be, this is the point. That's the x-intercept of that, the tangent line colored by the pink. Okay, colored by pink, and then it's gonna P sub n minus 1. Okay. So now you understand how the Newton's method works. So give other example. So think about this. What is this graph of f of x? Let's say here is let's say here's a p. We want to find out p. Let's say this is the initial approximation. Okay. Then we're going to find out the tangent line of f of x at p0, p sub p naught. Okay. So now then that intercept, we're going to get x-intercept right here. That's going to p sub 1. And then we're going to find out tangent line of f of x at p sub 1, which is this. Okay. So now what is going to be p sub 2. And then we're going to find out tangent line f of x at p sub 2. Okay, doing this, then that sequence approach p. Okay. All right, so now then algorithm is this. This is pseudo code. Okay. So input must be p naught and then tolerance and n naught, and the output must p or message failure. Okay. So here output p means the approximation. Okay. So or you can just your code, maybe your code return the sequence. And the step one set I equals 1, and then I is just increase until I is the I equals n0. N0 is the maximum number of iterations. Okay. So now and then while I is less than or equals n naught, do step 3 to 6. Now step 3, yeah, therefore we calculate the next value in the sequence. Okay, p sub 1. So p sub 1 is computed by Newton's formula. Okay, p naught minus f p naught over f prime p naught. So here you have to compute the f prime manually, okay, by hand, and then enter the that function into the code. Okay, keep in mind this. And then we measure the absolute value of p and p naught. If this is less than tolerance, then stop. Okay, and then your code return the what p0 and p1 or just p1. Okay, and then we increase I. Okay, and then set p0 to p. It means to update the p0. So what we got here, actually, that p represents p1 in first iterations. Okay, and then once in the step 5, increase I. Okay, so I now after step 5, I becomes 2, right? Now then we we put the the value p, which represent p1 in first iteration, into p0. Okay, so now then next iterations, that p becomes what? That p represent p2, and then that p0, actually that means that p0 means p1, right? So just repeating this one, okay, over and over, okay, until I reach to n not maximum number of iterations. Okay. So now then here note Newton's method is a functional iteration technique of the form Pn is equal to g of Pn minus 1. It makes sense, right? Here function g is defined by what? P sub n minus 1 minus f of p. Yeah, right here. Okay, right here. Okay. So now Newton's method is the special case of fixed point iteration. A functional iteration technique is nothing but fixed point iteration method. Okay. So now the Newton's method is a functional iteration technique that was used to give the rapid convergence we saw in part in example 3 and section 2.2. Yes. So now Newton's method cannot be continued if f prime Pn minus 1 equals 0. Why? Because look at the Newton's method, f prime is in the denominator. You see? Right here, you see? F prime is denominator. So, yeah, right here, f prime of P n minus 1 is denominator right there. So f prime is equal to 0, then yeah, you're going to get error. So the method is the next. The method is most effective when f prime is bounded away from 0 near P. So um, because the f prime is the what f prime is 0 near P, then we're going to get big problems because f prime is 0. Told you the Newton's method cannot be continued, right? Okay, so yeah, that totally depends on the behavior of function f, but f is, you know, the x-intercept of function f near the x-intercept function f, the the f prime, if f prime is not 0, okay, I mean away from 0, then Newton's method works really very well. Okay, so example 1. So let f of x is defined by cosine x minus x. Okay, so we want to find the root of the root. Let's find the root, but cosine x minus x equals 0. That's just root finding problem, right? So now then we convert this one to, I mean, reformulate the root finding problem to a fixed point problem like this: cosine x equals x. So now if you can find out certain x value satisfying this one, cosine x equals x, then what, that value must be what, root, right? So now just give me a second. Yeah, so we're using the fixed point iteration. then with the initial approximation pi over 4, the best result was 0.74. Using the Newton's method, okay, so then with the same initial approximation pi over 4, the best result is 0.739 right there. Okay, so please the implement, so just right, you have to write your own code, okay, and then implement these problems to check whether or not you're going to get same result. Okay, the note in example one, we don't see the effectiveness of Newton's method rather than the fixed point iteration. So you see that 0.74, 0.739, I don't think there is a big difference. But so, and also we have to check the number of iterations. Okay, so but anyway, see, because we assume that the p minus p0 is really small, so that p minus p0 square can be deleted in the Taylor series, so derivation of the Newton's method. However, in some instances, even poor initial approximation will produce to the root. Yeah. So now then, that totally depends on the behavior of f. Depending on the behavior of f, even the poor initial approximations, that will lead to the root, or completely different the solution. Okay, and then this one here. Okay, so now give me a second. And then also the actually initial approximation pi over 4 is 0.785. Okay, so 0.785, not really second, see. So 0.785, so p minus p0 is what? Let me see. Give me a second. Yeah, it's p minus p0 is yeah, we can say that really small. I mean, definitely less than 1. Okay, so this double the inequality means really, really small. Okay, so really close to 0. Okay, but not really close to 0, but actually it's okay. Yeah, so now then, so we can ignore p minus p0 square, this one, yes, but give me a second. Give me a second. So, but I'm sure that when you implement Newton's method, then you get the that result with a much less either number of iterations than fixed iterations. Okay. So now next one, the theorem 2.5. Okay. So now we're gonna mathematically we're gonna figure out why that formula, Newton's formula, works very well. So let's say f is in C2, and then p is in a comma close interval a comma b, and then f of p equals 0, so that p means p is a root, and then f prime p is not equal 0, definitely f prime p not equals 0. And then there exists delta such that Newton's method generate a sequence. Okay, and for any the p not means what? An initial approximation. Okay. So there exists what delta. I mean, so there is what's delta? Delta will, you know, will guarantee that good initial approximation. I mean, to guarantee that there existence of what initial approximation that generate uh, the sequence developed by Newton's method. Okay, so here's an example. Well, an example proof. Okay, so this theorem 2.5 proved the existence of the what? The, the sequence. Okay, so the definitely what? Okay, let's see. Okay, so let p sub n equals g sub pn minus p of g of pn minus 1, and the g of x is defined by x minus f over f prime. So k is in between 0 and k is in open interval with 0, 1. And then we'll see. Let's see the first we find the interval p minus delta, closing number p minus delta, p plus delta. Then the map from p minus delta comma p plus, we find the interval, and then that function g map from p minus delta comma p plus delta to p minus delta p comma p plus delta. So that means g is a function mapping from the, that interval to itself, right? And then the after the value of g prime is bounded by k. K is between 0 and 1, right? Right there. Okay. So what does that mean? This is what the actually assumption theorem 2.3. Excuse me. So remember that theorem 2.3, this fixed point iteration, a theorem about fixed point iteration, right? It's called fixed point theorem, actually. So now to see, now next one, look at the lemma. 1. Let f is continuous and then p is in the belong to a comma b. Suppose f of p is not equal to 0, then there exists delta such that f of x is not equal to 0 for any x right there, and then that is subset of a comma b. Yes. Okay. So then why? How can he so we'll see. Give me a second. So here in the proof, first we the main goal is to show that the function g satisfies the all the assumptions theorem 2.3, so we can use the conclusion of theorem 2.3. So first one, we need to find out the delta such that function g is defined. You see that here, function g right there. So g of x is defined by x minus f over f prime. So we gotta find the function g is well defined. Defined. It means that we have to find out certain intervals such that f prime is not equal to 0. Okay. So then, first one we find a certain interval, and then we show that g prime, f of g prime is bounded by k. Third, we're gonna show that function g on that interval. Okay. So definitely we have to find out delta. Okay. That's the first step. Okay, once we figure out the delta, okay, then we show that the absolute value of g prime is bounded by k on that interval, okay, p minus delta, comma p plus delta. And then third step, we have to show the function g uh, is a function mapping from p minus delta, comma p plus delta to itself. Okay, so to do that, we're gonna use the lemma 1. So f is continuous, and then p is in opening of a comma b, and then suppose that f of p is not equal to 0, then there exists delta such that f of x is not equal to 0, and then for any x on in the closed interval p minus delta, p plus delta, there is a subset of the closed interval a comma b. What that means, this is really obvious. So what that means, so think about the function. Let's say this is x-axis, and then let's say this is a graph of the f of x. Okay, so now then function f is the bound is continuous on closed interval a comma b. Let's say here is a. Okay, so right here is closed interval and the b. So you can see the function f is continuous function on closed interval a comma b. And then let's pick the p right here. So p, and then so that as you can see that p comma f of p, and the f of p is not equal to 0, right? And then since this is a continuous, there is an interval. There exists a delta such that, let's say this is the p minus delta. Let's say this is a p plus delta. There is interval p minus delta, p plus delta, such that what f of x is not equal to 0 on that interval. So it makes sense, right? So for here, on that interval p minus delta, p plus delta, in this interval, what their function value for any x value in this interval, f of x is not equal to 0. There exists such a delta. It makes sense because the function is continuous, right? So now we're gonna apply that lemma 1 into the f prime. Okay, so f prime is continuous, yes. Okay, you see that look at the assumption in theorem 2.5. Function f belong to the what? C2 up to second derivative function. Second derivative of f of x is continuous on closed interval a comma b. So f prime must be continuous, and the f prime p is not equal to 0. Okay, so see right there. You see that f prime p is not equal to 0. We'll see that here. Okay, so just look at this one carefully. Okay, we may deal with this one later in other theorems. Okay, f prime p is not equal to 0. So f prime is not equal to 0, right? And then by the lemma 1, so what's assumption lemma 1? Function is continuous. Okay, and then f of p is not equal to 0. Okay, yeah, right. So then there exists delta 1. Okay, to distinguish with the that symbol delta. Okay, so let me use delta sub 1. Okay, so that delta sub 1 is a specific value number. Okay, real number. Okay, there exists delta sub 1 such that f prime is not equal to 0 for any x. Okay, just miss the for any the symbol for any x belong to p minus delta 1 comma p plus delta 1 p plus delta 1. So now on that interval p minus delta 1 comma p plus delta 1, in this closed interval function g must be defined, right? So function g of x is defined. Okay, and then so that function g must be continuous. Okay, on that closed interval p minus delta 1 comma p plus delta 1. So now we're going to show that g prime is bounded by k. Okay, so what's a g prime? Since the function g is defined by x minus f over f prime, so we just take a derivative of the right-hand side with respect to x. Okay, so derivative of x with respect to x is 1, and derivative of this fraction using the quotient rule, you're going to get this. Okay, so what happened to the f prime, f prime? F prime times f prime is f prime square over f prime square, which is 1. So 1 minus 1, 0. Okay, so we're going to get this f times f third prime over f prime square. Now, remember that in assumption in theorem 2.5 right there. So f it belong to C2. So the what? So f is belong to C2 for any x. Actually, f is what? F is belong to C2 in on the closed interval a comma b, and then since p minus delta 1 comma p plus delta 1 is the subinterval in the close of the closed interval a comma b, so f must be what? F must belong to C2 for for any x on that closed interval, and then g prime is defined, right? Okay. So now then g must be C1, right? And on this closed interval, p minus delta 1, p plus delta 1. So there exists g prime, and then g prime is continuous. Okay. So let's see. So for first one, what? The first we found the specific interval p minus delta 1 comma p plus delta 1 such that so that a function what the f prime is not equal to 0. Okay, on that interval, and then in this interval we so that function g is defined in this interval because f prime is not equal to 0, and then we found the g prime. Okay, and then since what g prime f is c2, it belongs to c2, and then f prime is not equal to 0 in the interval p minus delta 1 comma p plus delta 1. So function g prime is also continuous. It means that g must belong to c1 in this closed interval. Now f of p equals 0. It makes sense, right? What's a p? P is a root, a function of the root finding problem f of x equals 0. Now we plug in p into g prime. What happens? G prime p is equal to f of p times f double prime p over f prime p squared. So f prime p is not equal to 0, right? You see that f prime p is not equal to 0. Why? Because please keep keep in mind that f prime p is not equal to 0. That's a big assumption in the theorem 2.5. And then f of p equals 0. That's also assumption in the theorem 2.5. You see that f of p equals 0. Actually, p is a root, right? So f of p is 0 and the f prime p is not equal to 0. So that fraction turns out to be what? 0 when x equals p. So g prime of p equals 0. Okay, g prime of p equals 0. Now they see here, then you see lemma 2. Let f is continuous function on closed interval a comma b, and then p is in a open interval a comma b, and the f of p equals 0, and the k is greater than 0 is given. Then there exists delta that absolute value of f is bounded by k for any x belong to that interval. This is also obvious. Okay, what that means right here. So think about yeah. So this kind of function f of x. Okay, so this is a continuous function on closed interval. Okay, so now like there. So think about, let's say here a, and then here's b. Okay, so as you can see, the f of is continuous function on closed interval a comma b, right? So this is belong to c closed interval a comma b, right? Well, now then you see, let's say this is a p right there. So as you can see that f of p equals 0, right? So f of p equals 0, right? Now what are you gonna do? Next one, then there the exists delta. So let me see from here to here. Okay, so let's say this is the p minus delta. Let's say this is the p plus delta. Okay, there is delta such that f of p is bounded by, so what's f of p right here? Let's say this is y-axis right here. So right there, this is going to be what? F of p plus delta. Okay, and then there's going to be f of p minus delta. Okay, so f is for any x in that interval, closed interval, absolute f of x is bounded by k, and then k is the given. Okay, for example, in this example, let's say k is just 1. Okay, then we can find out the such a delta so that absolute value of f is bounded by 1. It makes sense, right? Okay, so because the function is continuous, right? So now then, actually lemma 2 and lemma 1 is kind of similar, right? Okay, as long as the function is continuous, then we can find out such a delta that the function value, you can find delta such that the function values is bounded by a certain, the certain k value. Okay, that's a lemma 2. Lemma 1 is what? Lemma 1 is we can find out what the delta such that f of p, I mean function f is not equal to 0 for any x in that interval. So actually lemma 1 and lemma 2 is really similar, but give me a second. Yeah, lemma 1 and lemma 2 is really similar. This is lemma 1, this is lemma 2. Okay, let's see here. All right, so the lemma 2 is a more specific case than a lemma 1. Okay, so let's say, give me a second. Yeah, we move to a lecture note. So now we're gonna apply the lemma 2 into G prime. Okay, so we did show that what G prime is continuous, right? And the G prime p equals 0. So if G prime p equals 0, we figured out that, right? And then k for given, okay, let me give k value, which is between 0 and 1. And then now then there exists delta. Okay, definitely delta must be bounded by 0 and delta sub 1, right? Okay, so now then G prime, absolute G prime is less than or equals k for any x in the closed interval p minus delta, p plus delta, k minus the delta must be less than delta 1. It makes sense, right? So now then, now we show that the function g map from, p minus delta comma p plus delta to itself. So how can I do that? We're going to use the MVT, mean-value theorems. So if x is in the closed intervals, then mean-value theorems imply that for some psi belong to x comma p, we have this. What's the mean-value theorems? Mean-value theorems, we haven't seen, we have, applied mean-value theorems a lot, the theorems, right? When you prove that. So, but yeah, we'll see. So g of x, our first one, we're gonna, the what? Let me, give me a second. All right, so here, let's say this is a graph of g of x, and then x p is given. Okay, I mean, so we there is cosine right there between x comma p. Okay, but anyway, so keep in mind this g of p equals 0. Do not confuse with this. G prime p is 0. Okay, that doesn't mean that g of p equals 0. Okay, g of p must be p. That's how we define g. Actually, this is x minus f over f prime, right? Okay, so now then, mean value theorem is this: the slope of the secant line passing through the 2 point x comma g of x, and then p comma g of p. Okay, so the slope is what? G of x minus g of p divided by what? The x minus p. Okay, that is equal. There is what? There is cosine between x comma p such that what? The slope of the tangent line, which is the derivative of g at cosine. Okay, this is cosine comma g of cosine. Okay. So now there exists the cosine such that what g prime of cosine is equal to the slope of the secant line. Okay, so g prime cosine is nothing but what slope of the tangent line at cosine, right? Then we take the absolute value, and then we got this g of x minus g of p over x minus p is equal to g prime of cosine, okay, absolute value, and then move the x minus p to the right hand side. Then we get this g of x minus g of p absolute value is times absolute value of g prime of cosine times x minus p. Oh, absolute value. So now then, by the lemma 2, we did show that g prime is bounded by k. So this is less than or equals k times what? X minus p. Since k is what? Between 0 and 1, so that must be less than x minus p. But g of p is what? Actually p, right? Okay, you see that? And then so the x also what? Since the x is in the that x is in p minus delta comma p plus delta. Keep in mind this delta is what? That delta is greater than 0 but less than delta sub 1. Okay. So since the x is in p minus delta comma p plus delta, so x minus p must be what? Less than delta. Does that make sense? Okay. So now then, and then g of x. Give me a second. So and then what? G of x. So we got this g of x minus p absolute value, which is distance between g of x and p, so less than delta. Okay. It means that what? G of x must be closed in must belong to closed interval p minus delta within p minus delta comma p plus delta. Right. So function g must be function mapping from p minus delta comma p plus delta to closing number p minus delta comma p plus delta. Right. So now then the now wait a second. That's the how so I just show that the how we prove the what function g is function g map from the p minus delta comma p plus delta to p minus delta comma p plus delta, right? So now finally we can use the conclusion of the fixed point theorems, theorem 2.3. Okay, so now satisfy maybe in your textbook the theorem number is maybe different, maybe 2.4 maybe. Okay, so the sequence Pn defined by this one is converts to P for any piece for any initial approximation. That's the conclusion of the fixed point theorems. Okay, so proof is done. So here's a note. Theorem 2.5 is important for the theory of Newton's method, but it is seldom applied in practice since it does not tell us how to determine delta. Yes, you see here, even though we figured out specific delta 1, right here, delta 1, actually what? We have to figure out specifically delta, which is, that delta that, by the, you know, by the lemma 2, we mentioned in lemma 2, using the lemma 2, we figured out there exists delta between 0 and delta 1. What is it? So you see, it's kind of yeah, it's not really specifically mentioned about that in the proof, right? And then in a practical application, P0 is selected and successive approximations are generated by Newton's method. Yeah. So then a major weakness, computational f prime at each iteration. Yes, that's really uh, the big bottleneck of that Newton's method. And then so to overcome the, you see, yeah, this is we could still, but even though we have to find the f prime, and then the initial approximation, the choice of initial approximation affect the performance of the Newton's method a lot. But still, Newton's method is a really powerful method. Okay, really the efficient method. Okay, but to overcome, the computation of f prime, this is really expensive. For simple function f, it's okay, but for example, if we don't know it's hard to find the f prime. It's gonna be a big problem finding f prime. So to overcome that problem, we're gonna suggest the secant method. This alternative way um, to find the root, but having the similar, the performance to Newton's method. I'm gonna cover this one next time.